I'm the president of SFI, and welcome to this Ulam lecture, and I'll get into that in a little more detail, but let me just thank a few folks. As always, Thornburg Investment Management for underwriting the series, the Lensic, of course, for hosting it, and now Enterprise Holding Foundation. I feel like an NPR newscaster. But these Ulam lectures are our flagship annual lectures, and they commemorate the life of a very prominent citizen of this town, Stanislav Ulam, who lived from 1909 to 1984. He was a Polish-American mathematician and nuclear physicist, and he worked on the Manhattan Project and made all sorts of interesting discoveries in the area of stochastic processes, and worked in pure and applied mathematics, and was also a person of wide cultural interest. And these lectures celebrate, I think, the spirit of Stan Ulam's life, with researchers who aspire to the full range of creative possibilities. And so we want them to be big thinkers and broad thinkers. And I know somewhere over there, Claire and Steve Winner are here, and Claire is Stan Ulam's daughter, so it's always nice to have them in the house. So thank you very much for coming, wherever you are. And I just want to say, that knowing Claire and Steve well, I mean, they are supporters of what we stand for at SFI, which is empiricism, science, and ideas as an antidote to superstition, ideology, and ignorance. And so, yeah, and especially important now. All right. And so before introducing Chris and the topics of these very important talks that are very timely, I think, now, I want to give you a quote from something that Stan Ulam wrote on the topic of the responsibility of the scientific researcher. And this is what he wrote. He said, "Even the simplest calculation in the purest mathematics can have terrible consequences. Without the invention of the infinitesimal calculus, most of our technology would have been impossible. Should we say, therefore, that the calculus is bad?" This is the moral dilemma of those of us working in areas that can be applied and are applied to all sorts of different ends. And computing is one of them, of course. Chris, who will speak tonight, is an SFI professor. His undergraduate degree was in physics and mathematics from Northwestern. His PhD in dynamical systems from Cornell. He was a postdoc at the Santa Fe Institute and a professor at UNM. But in case you think we're all sort of ivory tower eggheads at the Santa Fe Institute, which we are, he was also city councilor of District 2, and many people in this town, yes, for many years, actually, and many people in this town say, "Chris Moore, but isn't he a politician?" No, he's a theorist. He's very well decorated. He's a fellow of the American Association for the Advancement of Science, a fellow of the American Mathematical Society, fellow of the American Physical Society, and he wrote a wonderful book with another faculty member at SFI, Stefan Mertens, called The Nature of Computation. It's published by OUP, and it's a huge, massive tome, but it's beautifully written and actually quite funny, which is surprising for a book of that nature. At SFI, I sometimes feel we have too many credentials and too many publications. But there are qualities of researchers that aren't as evident to the outside world, because what is typically consumed is the science. I just want to point out that when I bump into Chris, which is often at SFI, we don't talk about science. We talk about the novels of Patrick O'Brian, the stories of Stanislav Lem and Jorge Luis Borges, and the relative merits of Blade Runner versus Blade Runner 2049. That's what we talk about. And I want to not be funny about it. I think these are actually, in many ways, the sources of our inspiration. And they're not revealed in the sort of final, ultra-filtered sake of our published work. And the saying is, sake drip-pressed in an ice igloo. That's the sort of the purest form, and I think it's good to see things in the raw. Chris lives at the intersection of mathematics, statistical physics, and theoretical computer science. And the important point is he doesn't just stitch or suture together those areas. We're not in the business of building Frankenstein's monsters. at the Santa Fe Institute. This goes under the euphemism sometimes of interdisciplinary science, which is absolutely of no interest to us. We're interested in foundational similarities, fundamental patterns that recur in nature across a variety of different domains, and seeking to formalize them with mathematics and computation. And in that endeavor, Chris is really one of the best. So that would include his work on dynamics on networks, issues of limits to inference when you have incomplete data, quantum computing and quantum algorithms, the computational complexity of physical systems, and even the application of geometric games to questions of mathematical proof and computation time. So tonight, Chris's title is Easy, Hard, and Impossible Problems, the Limits of Computation. And it's not hard to think about an easier way of limiting human potential than imagining that computers are unlimited. So, Chris. Thanks.
Thank you very much for being here tonight. So I thought a lot about what I wanted to say to this general audience. Unfortunately, I don't have the symphony behind me tonight as a backup band. Some of you are probably here for that. When I look around at the world, it seems like in many places we're in danger of going backwards, that we're giving up on a lot of the progress that we've made over the past century or so. And petty prejudices that I thought were dying the quiet death they deserve have come roaring back into life. These prejudices divide us. They make it impossible for us to learn from each other, to empathize with each other, or certainly to solve our problems together. And I honestly believe that science, along with music, art, literature, all the ways that we express the human spirit, that science is one of the most powerful antidotes to this slide backwards into tribalism. And by science, I don't just mean the mass of scientific knowledge that we've been able to build up so far, although as a species we should all be very proud of that. I also mean the culture of science, the practice of science. Scientists, although we're humans like anyone else, are trained to do some really good things that most people don't do, like admit that we might be wrong. Admit that we have more to learn. You know, we don't always live up to these ideals, but these are our ideals. And simply by being here tonight, you've shown that you're members of this part of humanity, that you're here because you want to know more, you think that learning more is a good thing to do, and maybe you even think that the more we learn, the better our chances are of creating a beautiful society and a beautiful world. So thank you very much for being here tonight. So I'm going to introduce you to a branch of science, or really mathematics, that you may have heard of. It's called computer science, but it is not the study of computers. It's the study of computation. It's the study of any situation, any system in which information is being transformed and in which problems are being solved. So it's really the art and the science of problem solving. And computers are not the only things that compute. Our brains compute, our cells and our bodies compute and communicate with each other. Some people even say that cities and organizations and markets compute. So any entity which is trying to find a good solution to a problem, that's what the study of my kind of computer science is. So as we're going to see tonight, there are some problems that are pretty easy, where you can quickly zoom in on a solution. There's some miraculous shortcut that lets you immediately see whether a solution exists. There are others that are fiendishly hard, that require you to search through a huge haystack, a huge space of possible solutions, and that might take you astronomical time. And there are still other problems that are impossible, that no computer program can solve, that in order to keep solving them, you need, in some sense, to be endlessly creative. So this is going to take us from some classic puzzles all the way up through the paradoxes that lie at the heart of modern mathematics. Now, tonight's a bit abstract. If you want to hear more about the impact of computational decision-making on human beings, you should come back tomorrow, when we'll be talking about the rise of algorithms and their use in the judicial system. And if you had a friend who couldn't make it tonight, you should tell them to come back tomorrow because tonight is not a prerequisite for tomorrow. All right, let's dive in. This is a puzzle. If you're the kind of person who likes puzzles, you may have seen it before. This is a map of part of Königsberg, now called Kaliningrad. And there's a river, the River Pregel, and there are 2 islands in the river and a total of 7 bridges that connect the islands to each other and to the 2 riverbanks. So the question here is whether it's possible on a Sunday afternoon, strolling around Königsberg, to cross each bridge exactly once. We need to cover each one but not retrace our steps. So let's see if we can do this. Why not? We could go up there, starting on that central island, then down over here, then over there, then up there, up, now we're stuck. Okay, well, let's see. Let's go back to the last place where we had a choice. We could go down over here, and then up there, and then over there. Now we're stuck again with no way to get up to the upper right there. Okay. I am carrying out an algorithm as I do this. What is an algorithm? Named after algoritmi. An algorithm is simply a method for solving a problem of a certain kind. It could be something that a human being does. It could be something that a computer program does. Now, the algorithm I'm carrying out here is try everything. Try all possibilities. And, well, okay, that is an algorithm, but it might be a relatively time-consuming one, especially if we were dealing with the bridges of Venice instead of Königsberg. So if you asked me this same puzzle about Venice, and I just said, oh, I don't know, try every possible path and see if any of them work, you might not be happy with me. A friend of mine at Pittsburgh says, actually, Pittsburgh has more bridges than Venice. So, in fact, for this particular puzzle, there is a much faster algorithm which avoids doing all this work of searching through all these possibilities. And it was brought to us by a mathematician named Leonhard Euler, who invented a whole new branch of mathematics, largely to deal with this problem. So his branch of mathematics is called graph theory, and we still use it today to study social networks, biological networks, food webs, transportation networks, and so on. So what he's done is he's taken the 4 locations that we had there, the 2 islands and the 2 riverbanks, and just made the map a little more abstract. So each one is now a single node in this little network, and each bridge is an edge between those 2 nodes. So now the game is, can we draw this, covering each bridge exactly once? It's a lot like the old puzzle of, can you draw this picture without lifting your pencil from the page and without retracing any of your steps? Okay, well, this is a new representation, but hasn't really changed our ability to solve the problem. Now Euler comes in with a wonderful observation. He says, according to the rules of the game, since you can only go across each bridge once, at every node, the bridges must come in pairs. If you enter along one, you have to leave on another. So they come in pairs. Enter, leave, enter, leave, enter, leave. Except maybe the first and last nodes where we begin and end our path. All right. Now, armed with that insight, all we have to do is notice that all 4 of these nodes, all 4 of these locations have an odd number of bridges. 3, 3, 3, and 5. So there is no path possible. We're done. Well, notice what Euler has done for us here. He's given us a much faster algorithm which released us completely from the obligation of searching through all these possibilities. And this algorithm of just checking the oddness or evenness of the number of bridges at each node would work perfectly well for the bridges of Venice. It would be pretty quick to check them all. So he's given us a very efficient way to solve this puzzle. And by the way, these are called Eulerian paths in his honor. So Eulerian paths are ones that cross each bridge once. Good. Now let me show you another puzzle which at first sounds almost the same. These are called Hamiltonian paths, named after a certain Hamilton who made a lot of contributions to mathematics and physics. Here the game is just a little bit different. Instead of crossing each edge once, we have to visit each node once. So if you've heard of the traveling salesman problem, there you have like a map of cities and you want to visit each one exactly once. So in this particular example of this puzzle, I've taken one of my favorite things, the dodecahedron, that's one of the Platonic solids, and I've squashed it to make the network on the right. And I want you to ponder for a moment if you think it's possible to start somewhere there and tour around on the edges and visit each place exactly once, maybe even come back to where you started. Not obvious how to figure this out. Well, there are lots of solutions. Here's one of them. Okay, so these are called Hamiltonian paths. And one of the reasons why we named them after Hamilton is that he unsuccessfully marketed a game where the first player chooses the first 5 steps of the path and the second player has to try to complete it. Now, the funny thing is that unlike the Eulerian path problem where we had this brilliant shortcut which immediately told us whether or not a path exists, here, essentially the only way we know how to solve this problem is by searching through all the possibilities. And how might we organize this? Well, it might look like this tree, where you take that first step and then there are 2 choices of what to do next. Each of those leads to 2 choices, each of those leads to 2 choices, and so on. And you would follow down this tree, systematically examining every possible path, until you might reach a leaf of the tree where maybe you've succeeded in solving the whole puzzle, or you've gotten stuck somewhere, and in that case, you would backtrack and try another branch of the tree, go back to the last place where you had a choice. Well, again, this is a perfectly fine algorithm, but there's a problem. So suppose that we're looking at a puzzle of this kind, but instead of just 20 nodes, we had n nodes where n is 100 or 1,000 or something. Well, if roughly speaking, the number of choices we have at each node is 2, the total number of choices we have to explore is 2 times 2 times 2, n times. The nth power of 2, 2 raised to the n. Now, this is an exponential function. I know that we like to say in popular culture, something is growing exponentially just because it's growing really fast. But for people like me, this has a precise meaning. It means that this function is doubling every time n increases by 1. Well, what's so bad about that? Well, let me take you back to middle school or high school and remind you about polynomials. So a polynomial is a function like n squared, that's n times n cubed is n times n times n. And if we have a method of solving a problem where if the problem is of size n, like it has n cities on the map, if we can do it in n squared or n cubed time, we're reasonably happy because even if n is 1,000, well, 1,000 squared is only 1,000,000. 1,000 cubed is only 1,000,000,000. And your computer does 1,000,000,000 things every second. So that's no big deal. On the other hand, 2 times itself 1,000 times, 2 raised to the 1,000th power, is this number, which is much bigger than the number of stars in the sky. So if the only method available to us costs this much, takes this much work, we're not going to solve our problem anytime soon. Let me give one more illustration of this polynomial versus exponential thing. So the simplest polynomial of n is n. It grows like n. Okay, we got that. N squared grows like the area of a square, which is n by n. N cubed grows like the volume of a cubical box, n by n by n. But here's another illustration of our exponential. Legend has it that the Emperor of India was so grateful to the inventor of chess for creating this fantastic new board game that he said, "I'll give you anything you want to reward you for this. What do you need?" And the inventor said, "Well, people in my village are kind of hungry. Could you please put 1 grain of rice on the first square of a chessboard, and then 2 on the next square, and then 4, and then 8, and then 16, doubling at every square?" And the emperor said, "Of course, make it so." And then someone, the grand vizier or the exchequer or the rice steward or someone had to say, "My liege, after only 20 squares, we have more than 1,000,000 grains of rice. After only 30 squares, we have more than 1,000,000,000. And after all 64, we have about 18.5 quadrillion. I had to count the commas there to get that right. And that's more than all the rice that has ever been or will ever be. So if that's the cost of solving a problem, it's going to be a very hard problem. So I'm trying to get across this idea to you that when we have a polynomial time algorithm, we have some shortcut, like Euler's. If we don't have a shortcut, we just have to search every possibility, we might be dealing with this kind of exponential cost, and that will be much more challenging for us. So to wrap this little section up, the Eulerian paths, crossing each edge exactly once, have a very nice Shortcut, just check that each node has an even number of bridges. You don't need to search. On the other hand, the Hamiltonian paths, is there, sorry, wrong Hamilton. The Hamiltonian paths, where we have to visit each node exactly once, not only do we not have such a shortcut, but as I will show you, we have very good reasons for believing there is no such shortcut, okay? It's not just a matter that somebody clever like Euler hasn't come along and shown us how to do it. There is no way to avoid searching through a vast number of possibilities. And this is the kind of distinction between easy problems and hard problems that people like me want to understand. So what is it about these two problems that make one so much harder than the other? Well, let me discuss another method for zooming in on solutions. It's a terrible method for almost every problem that you or I will ever meet. It's called a greedy algorithm, and it lives in the moment. What it does at every instant is make the move that seems in the short term will make the most progress. It never thinks ahead. It never plans ahead. It's the grasshopper. Anyway, so this type of algorithm goes back to a gentleman named Otakar Boruvka. I hope I'm getting that right, who in the 1920s was designing an early electric power network for towns in his native Bohemia. Now, he wanted to connect all these towns with electric wires, and if you just want to make sure that there's one path from each town to each other town, you don't need a loop, because that would give you two ways to get there, right? So all you really need is a tree that stretches out and connects all the towns to all the other towns. Actually, this is a terrible idea for a power grid, because if one of these edges gets cut down by a falling tree, then it would break into two pieces. So it has no redundancy or resilience or any of that, but okay. So he wanted to find the tree. This is called a spanning tree in graph theory, the branch of mathematics that Euler invented, with the smallest total length of all the power lines, right, to minimize the cost. Or if you prefer, maybe some of them might go over some mountaintop and that would cost more. So you can think of it as the smallest total cost if you wish, but let's talk about length. So he came up with this algorithm which seems incredibly naive. All you do at each step is connect the pair of cities that has the shortest link between them that won't complete a loop because we don't need loops. That's the whole algorithm. So let's see, we'll start with that pair in the middle, and then maybe that pair over there and over there. Now we kind of have some ties. And anyway, so this algorithm proceeds. Now we have a spanning tree. We have a network which does connect all the cities. But is this the best possible? I mean, why should we believe that this very naive algorithm, out of all the spanning trees which might have connected them, managed to find the one with the smallest total length? Well, for this particular problem, amazingly, this works. I can kind of sort of show you the proof, actually. So suppose that the algorithm wanted to add that link up there, which I call E for edge. But for purposes of argument, let's suppose that the one it should have added was a different, longer one down there, E prime. Well, add both. Now you have a tree with a loop, but now you could cut E prime, and you would still be held together by E. But remember, our assumption was that E was shorter. So that was good. You now have a spanning tree with a smaller total length, and the algorithm was right all along. Got it? That was a proof by contradiction. So for you St. John's people. So for this particular problem, this algorithm works, which is surprising. I mean, when you're playing chess, I'm not very good at chess, but sometimes you have to, I don't know, sacrifice your rook so that you can save your queen later or something, or win the game 3 moves later or something. So in almost every situation, certainly all the problems that we deal with in society or the environment, you need to think ahead. And you sometimes need to make sacrifices. You sometimes need to make things a little bit better or a little bit worse in order to make them better later on. Now, there are lots of other problems in computer science where greedy algorithms totally fail. So for instance, here's the traveling salesman problem. So there used to be these people called traveling salesmen. They had suitcases, they had families. They went from town to town selling things. This was a long time ago. So suppose we start out here in the lower left. Now, a greedy algorithm would go to the nearest city that you haven't been to yet. That would be the kind of short-term thing to do. But if you do that, you follow this path and then say, oh no, we skipped Topeka. We have to go all the way back here, and that's going to cost us about twice as much as what we should have done, which was be less greedy and go out of our way at first, make a little sacrifice, cover that city, and then handle the rest of the chain. So, what have we learned from this? We've learned that these two problems, which are not so different on the surface, connecting things with a tree or connecting them with a path, for one of them, greed is good, and for the other, it often leads us down the primrose path and takes us in the wrong direction. What makes the difference? Well, there is a concept which shows up in a lot of sciences called the landscape. So imagine the landscape as this vast space of all possible solutions to a problem, and the height of wherever you are is the quality of that solution. Well, some landscapes look like this. We call them Mount Fuji landscapes, seriously. There's one great solution which dominates the landscape, and there's a simple, reliable way to find it. Start anywhere on the mountainside and walk up. It doesn't really matter how good you are at walking up or which way you walk up if there are several choices. Just keep walking up, keep making little improvements. And the nice thing about this is it works even in the fog, because after all, you don't have a map of all the solutions. If you did, that would make things too easy. So even if you don't know what your options are, even if you have no idea what the world of possible solutions looks like, if you just keep making little improvements, you're guaranteed to reach the summit. You know, shortly after I first moved to Santa Fe, I was hiking with some people, and I said, I'm tired, I'm going back home. And I forgot that for going down, this doesn't work. There are lots of ways to go down, and some of them lead you out onto some county road where then some nice person picks you up with a truck before you die of thirst. Anyway, now, so for this type of problem, if this is how the landscape is structured, you can start nearly anywhere and make whatever greedy improvements you can make, and you'll find the summit. You'll find the best solution. But of course, most problems look more like this. We have lots and lots of options. We have lots and lots of solutions. And maybe the best one is a little bit better than the one over here. But if you start in a random place, and again, without the benefit of a map, and you just start walking up from wherever you started, you almost certainly won't find that highest mountain peak. You'll get stuck on some smaller peak. You'll get stuck in what we call a local optimum, a place where if you make any small change, any small motion away from where you are, you'll make things worse because you're stepping down off that peak, okay? So small changes are not going to improve the solution. There is some huge change that would cause you to jump all the way over to the summit first, or perhaps first go through a valley where things would get much worse before they got better. The problem is that it's worse than this picture suggests, because it's not just a 2- or 3-dimensional landscape, it's some kind of high n-dimensional landscape, and again, we don't have a map. So you don't know how to get to the summit, and this forces you to explore. You have to do a lot of exploration. And somehow this is what makes a lot of the problems we need to deal with hard. Now, I should mention that this happens even in other sciences. For instance, in ecology, we talk about the fitness landscape, where species are trying to evolve by mutating a bit, and they want to maximize their chances of survival and the chances of survival of their children. In physics, things like to settle to low energy states. So we flip the landscape over, and now valleys are good and peaks are bad. Anyway, so you know, rocks roll downhill in physics. So if next time you're looking at a window, well, that window glass is made of pretty much silicon and oxygen. It's basically sand, which has been melted and then cooled back down. It turns out that the state it really wants to be in is that one on the right, a perfect crystal. That would be the lowest energy state. That's kind of the solution to the problem that the atoms are trying to solve. But they never find it. Instead, they get stuck in a much more jumbled state. In fact, if you look at window glass on an atomic level, it looks more like a liquid than like a crystal. So why did it get stuck? Well, maybe some of the atoms on the left were trying to line up with each other. They were trying to solve their part of the problem. Some of the ones on the right were trying to solve their part of the problem. But these two solutions that they found to their parts of the problem aren't compatible. They don't knit together to a solution of the entire problem. Maybe this sounds familiar to you. So in order to get to that perfect crystal, we would have to pay a huge cost, a big rearrangement of one of these parts, greatly increasing the energy before it could fall into place with the other part. And so this is a problem where literally the atoms are trying to solve, they're having trouble computing where they ought to be, and they get stuck for a very long time. All right, good. So what's next? Well, let's go back to our Hamiltonian path problem. Finding a way to tour this network and visit each node once may be hard, but if I show you the solution, all you have to do, it takes a glance, is say, oh yeah, it goes around and yeah, it visits everywhere, it works. So for this problem, you can check solutions. They might be hard to find, but they're easy to check. That's not nothing, right? Because for a lot of problems, it's even hard to tell when you have the right solution. So, if God gives you a solution in a dream or you trip over one on the sidewalk, you can at least make sure that it works. So this brings us to these things that we call complexity classes, P and NP. P stands for polynomial. Those are the ones that we know how to solve pretty quickly without a lot of search. NP are the ones where we can check solutions quickly. Doesn't mean you can find them, but you can check them. We like to use this metaphor of a needle in a haystack. You know, you could have a huge haystack of possible solutions to a problem, and it might be very hard for you to find the needle in it or to tell if there is a needle in it. And yet, if you pick up a particular thing, you can prick your finger with it and check to see if it works. Okay. Now, this gives us a kind of map of possible problems. So P down here contains Eulerian path, the spanning tree problem we saw that Boruvka came up with. Hamiltonian path lives up there, and in fact, we think it's kind of near the top of NP. It's in a class we call NP complete. These are the hardest problems up there. So these are the ones that we think that it's really hard to find the solution, and I'm going to explain to you why. So in order to explain to you why we believe so strongly, except for a handful of heretics, why we believe so strongly that these problems are really hard, I need to explain to you a bit more about the innards of a computer. So, of course, they're ubiquitous, but what are they doing inside them, in their guts? So, you know, we know intuitively they're dealing with numbers, symbols, all sorts of things, but at the root level, what they're dealing with are things called bits. Bits aren't even numbers. They can only take two different values, 0 or 1, or on or off, true or false. That's all they can do. So everything is made in bits in a computer. And now, just as there's arithmetic we can do on numbers, we can add two numbers and get a third, we can multiply them and get a third, there are things we can do to bits. They're called and, or, and not. So for instance, I could take two bits, combine them, and get a result which is true, it's on, only if both of these bits were on, this one and that one. That would certainly come in handy sometime. Accelerate the car if the driver's foot is on the pedal and there's no one in the crosswalk. Then we can also do the or, where the result is true if either one, or possibly both, of the inputs are true. And then finally there's not, which flips the switch and changes on to off and vice versa. So if you were to look at a circuit diagram in a computer, you might see something like this. Each of these is made of a couple of transistors, and these are little and or gates which are taking bits and combining them and spitting out the result and somehow doing some job for us, computing something. So here's what the AND gates look like. They're the round ones, and again, if both of the things going into it or either one are 0, then it puts out a 0. But if they're both 1, it puts out a 1. And an OR gate, if they're both 0s, it puts out a 0. But if either one or both is a 1, it puts out a 1. So these are the basic elements inside every computer. And when we compute something, whether it's, does watching a YouTube count as computing something? Whenever we do anything on a computer, it's breaking it down into these tiny pieces, these tiny steps. Now I'm going to tell you about something completely different. Hold what I just said in your mind, okay? Because this only seems different. So here I have a map of South America, and I've colored it as is traditional to avoid confusion. Whenever two countries meet at a border, I've used different colors there so we can see the border clearly. Now, there's an old result in mathematics that 4 colors are always enough. Here I have red, blue, yellow, and orange. So this actually took a really long time to prove. It was suggested in the mid-1800s, and it wasn't proved until 125 years later, in the 1970s, that 4 colors are enough. It's called the 4-color map theorem. And in fact, it's kind of controversial because the best proof we have still involves a lot of computer assistance to check a bunch of cases. So not everyone regards it as a good proof. So therein lies a tale. Anyway, but for some maps, 3 colors are enough. Is that true for this map? Could I change the colors and reshuffle things and maybe get rid of the orange and just have 3 colors? That's a puzzle. I'm going to try to show you why this puzzle can be very hard. So, but first I'm going to transform it into another kind of question on networks. Like Euler did, I'm going to have a node corresponding to each country, and then whenever 2 countries share a border, I'll draw a link between them. So now the question is, can I color the nodes of this network so that no 2 nodes are the same color if they have a direct link? Okay. Well, here's another puzzle like that. I changed the palette, blue, purple, and yellow. I've colored some things in already. Let's start with that one on the bottom. I think I'll color that purple. Well, I only have 3 colors to work with, so the one to the left of the one I just colored, see it's in between a blue and a purple? Well, it better be yellow then, because it can't be the same as either of those. Well, the one above those 2, the blue and the yellow, had better be purple. That one had better be blue. Things are going well. I think I'll color the one on the left of the middle there yellow. Oh, now I'm stuck because I've taken all 3 colors from the one to the right. Okay, I'm not dead yet. I'll move the yellow one over there. Then this one can be blue. That one has to be yellow. That has to be purple. Now I'm stuck again. What am I doing here? I'm crawling around, well, hopefully walking around on that bumpy landscape. So I've gotten stuck at a little mountain peak. I haven't solved the entire problem. I've solved most of it, but now I'm stuck. And indeed, no small change I can make is going to make things any better. I have to go all the way back. Oh, yes, that's what I was just saying. I have to go all the way back to when I colored that one on the middle of the bottom purple and recolor it blue, and now everything works. Okay, why is he telling us this? Because I've designed this puzzle so that it is sneaking in some computation. This thing is actually an AND gate, where the blue things are 0 or false, and the purple things are 1 or true. And there's the AND gate, and it has those 2 inputs and that output. And as you recall, if an AND gate has a 1 and a 0 going into it, because those are not both true, it must output a 0, so that one must be blue. So what am I saying? I'm saying that I can disguise computation as coloring puzzles. I can sneak computation into this puzzle about coloring with 3 colors. And that should tell you that it's not so easy to tell whether I can color things with 3 colors, because I could be doing, sneakily, some complicated computation in disguise. And indeed, once I have one of these, I can wire them together and make a big network, which is actually, well, it could be searching for a traveling salesman tour of less than 10,000 miles up the eastern seaboard. It could be solving our original Hamiltonian path problem. It could be doing all sorts of other things in disguise. So that suggests that this is not so simple a kind of puzzle. Well, having shown you how to compute with colors, let's change slightly to computing with cats. I'm a cat person. Here is a puzzle of wooden pieces that are carved to look like cats. More abstractly, if you're not a cat person, these are pentominoes. You've heard of dominoes. Dominoes are 2 squares stuck together. Pentominoes, from the Greek penta for 5, are 4 squares stuck together. You can make a bunch of different shapes out of those. And if you're like me, then you enjoy trying to fit these into some shape, and you're proud if you make it work. Now, how do these puzzles work? Well, you often solve almost all of them, and then you get stuck. And there's a shape for the P-shaped kitty, but the one you have left is the S-shaped kitty. And you have to rearrange everything and toss it all back out onto the coffee table to get it to work. Bumpy landscape, okay? Stuck on those little mountain peaks. Now, why are puzzles like this tricky? Because even with these simpler shapes, which I was able to find after some effort pictures of cats to fit in them, even with these simpler shapes, we can do computation. Again, we're going to sneak it in. We're going to design shapes where there's a kind of wire which can be filled in with the elbow-shaped kitty either this way or that way, and that will mean true and false. And then we come up with some junctions which act like AND and OR gates so that solving this puzzle corresponds to carrying out some computation. So again, that's why we think this type of puzzle can be hard. Because I focus so much on Hamilton, you can do this even with Hamiltonian paths. Remember, the rule is we have to visit each node once. I put arrows on the edges that you have to follow. I don't want you to go backward. Forgive me. So the question is, can we get all the way from the top to all the way at the bottom? Well, there are these 3 things that look kind of like rope bridges. But because you can only visit each node once you start across them, you have to keep going in the same direction. Well, that will be my true and false. Why not? And then I'll add that little thing on the side so that after you choose values for these 3 bits, let's call them x, y, and z, and after we say that maybe going from left to right is true and right to left is false, then, well, you have to visit that node on the side. That's one of the rules of the game. But I've arranged the arrows from these bridges so that you can only visit it if x is false, or if y is true, or if z is true. And once I can build that kind of thing, I can build AND and OR gates, and I can build a whole computer out of this. So, computing in disguise. If any of these problems were easy, if any of these problems had a shortcut, like Euler's shortcut, then, well, for one thing, thousands of other problems would also suddenly be easy, because I can disguise thousands of other problems like these. These problems would also all be easy as each other, because they can also be each other in disguise. Why not? Now, would this be a good thing? If I could solve all these tricky puzzles very quickly without having to search, without having to get stuck, without having to tear my hair out at the coffee table? Well, it would mean something profound. It would mean, remember that NP was this class of problems where solutions are easy to check. Okay? If any of these problems were easy, it would mean that anything which is easy to check is also easy to find. That sounds odd. Again, think of the needle in the haystack. Just because I can prick my finger with a needle and check that it actually draws blood doesn't mean that I can magically find it in a huge haystack. Let's say I don't have a magnet. So it sounds strange to think that anything which is easy to check is easy to find. We don't believe that's true. Now, some people would find it convenient. The traveling salespeople would have better routes. It would be easy to pack your luggage in your car. You wouldn't have that situation where you fit in almost all the suitcases and then there's the wrong space and you have to throw everything back out on the driveway. You wouldn't have to deal with that bumpy landscape. Also, code breaking would be really easy. Because after all, if I intercept a message that you've sent to your friend and I manage to figure out the secret key, I usually know when I've got it right? It says, meet me under the banyan tree at 3:30 a.m. or something like that. I'm like, aha, I got it right. It's not just gibberish. Well, if P and NP were the same, then all codes would be easy to break, almost all, because anything which is easy to check is easy to find. So we don't believe this. We think this is crazy talk. One of the biggest reasons we think this is crazy talk is that science would be too easy. This I could not bear. So here's Johannes Kepler, and he looks through his telescope and he checks the numbers really carefully, and he has a brilliant insight. He says, they're going around in ellipses, not in circles. Brilliant thought. But it's pretty easy to check afterward. Just, run the numbers, and it's like, oh yeah, you're right, they're ellipses. Here's Lynn Margulis, who had a brilliant thought in biology that a lot of the little organelles, the little machines running around in our cells, were at one time independent organisms, which were then in a symbiosis with us and then got swallowed up. Brilliant thought. Once you have that thought, then you look around and there's a lot of evidence for it. I refuse to believe that everything we can check post facto like this, that we can find evidence backing it up afterward, is easy to come up with in the first place. Then we wouldn't need people like Lynn Margulis and Johannes Kepler to have great ideas. We wouldn't need cleverness and insight. So that's what I think about that. Now, we've talked about easy problems and hard problems. What time is it? Oh, good. Let's talk about impossible problems. So we've talked about problems that there's a quick shortcut. We've talked about problems where there's an enormous amount of searching to do. Are there problems that can't be solved by a computer no matter how much time you give it? Well, let's delve a little bit into the history of computers. So here's Charles Babbage, who, by the way, hated street musicians. And he proposed a mechanical computer, which was never quite built. I've seen pieces of it in the British Museum, and it was, there was a version of it built out of Meccano, that's that kind of advanced Lego erector set type stuff. Anyway, it didn't get built in his lifetime, but Ada Lovelace studied it and studied his designs. And in addition to being the first person who wrote a complicated computer program for it, Ada also had an insight which is kind of part of the air we breathe now, which is that if you have a computer that can represent numbers, then it could also represent lots of other things, for instance, music. So she talked about, oh, if you could build this, maybe you could find some ways to generate new musical compositions. So the world we live in now, where data works equally well to represent pictures, videos, audio, music, text, stories, and numbers, that was Ada's vision of where this was going. And I think that may be why, in a steampunk universe, she and Babbage have formed a crime-fighting team. You can buy that online. Okay. All right. Sorry, I just want that to run another moment. Okay, good. So now, as the 20th century wore on, people were really trying to understand what are computers capable of, and this was intimately bound up with studying the very foundations of mathematics, logic and set theory, the things that are kind of down there in the, in the sub-basement of mathematics, underneath the geometry and the algebra, trying to make sure that the logic holds together. And to study this, you often need to deal with paradoxes, with things biting their own tails, or maybe Mobius strips coming around and meeting themselves with a twist, so that every time you go around it, you find yourself on the other side of what you thought you were on. Because these paradoxes reveal things to us about what actually makes sense, and sometimes reveals to us that things we thought made sense didn't make sense. So here, for instance, is the classic Epimenides the Cretan saying all Cretans are liars. If he's lying, he's telling the truth. If he's telling the truth, he's lying. Actually, this isn't a paradox at all. Do you know why? It could be that he's a liar, but that lots of other Cretans aren't. See, because then he's lying. They're not all liars. Then there's no paradox. Anyway, for some reason, people often miss that. Here's another paradox that was brought up by Bertrand Russell, the philosopher and one of the founders of set theory. Here's the English version. You probably heard it. The barber shaves those and only those in town who do not shave themselves. Does the barber shave themselves? Well, if they do, then we've just been told that they don't, and if they don't, we've been told that they do. So something's wrong. Now, for Russell, this was not about barbers. It was about sets containing themselves. So he was trying to understand, again, set theory. A set could be the set of this podium, the numbers 1 through 7, the color blue, and how about itself? Can it belong to itself? Well, if you have sets that belong to themselves, then you can get in this kind of trouble where you ask about the set that contains all sets that don't contain themselves. Got it? Does if it doesn't if it does. So these are not just little games. They reveal to us that we have to be careful as we figure out what the mathematics is of sets, which are very basic objects in math. Anyway, so these paradoxes help reveal things to us, and a whole slew of people in the 20th century, David Hilbert, Rosa Peter, Alonzo Church, Julia Robinson, and many others, were trying to understand the foundations of mathematics and at the same time the foundations of computation. Julia Robinson is worth mentioning because there's a wonderful science, technology, and engineering and mathematics festival named after her, and she also had this lovely quote. I won't read the whole thing, but she says, "I think of mathematicians as forming a nation of our own without origin, race, creed, sex, age." It's a lovely thought. I think it's not a coincidence that scientists and mathematicians prefer to build bridges than walls. It's just kind of how we are. Okay, so here's Alan Turing. Now, you've probably heard of him because of his heroic work in cracking the Enigma code that the Nazis were using during World War II. And this played a major role in the war. Sad to say, he didn't stay with us very long after that because he was persecuted by his society for being homosexual, and that drove him to suicide. And much too late, many years later, the Prime Minister of England apologized for this and said, look, you know, this person played a key role. The war might have gone very differently if it hadn't been for his code breaking. I'm deeply sorry. Yeah, well, yes, I am too. I often wonder what computer science would be like now if Turing had lived a whole lifetime with us. Because in addition to code breaking, he did many other things. For those of us at the Santa Fe Institute who study complex systems, he's kind of a hero because, for instance, he figured out how the leopard got its spots. So he mathematically modeled chemicals getting concentrated and interacting with each other and flowing from one space to another and figuring out how zebras get stripes, and I guess this is actually a jaguar, get these spots. So that was amazing. They're still called Turing patterns in his honor. He also wrote one of the early and very important papers about artificial intelligence. So he contemplated, you know, this is very early in the age of computers. They were not very powerful by modern standards. But he was contemplating, will there ever be an intelligence coming out of these computers? And he was very far-seeing in this, in that he predicted that if we ever do, that it'll be more like raising a child than like programming a computer. And this is indeed how neural networks work now. We don't program the neural network. We don't say, do this and do that. We give it lots of data, lots of examples, and then it trains itself or learns what it should do. There is a poignant paragraph here where he says, the child could not be asked to go out and fill the coal scuttle, and one should not send it to school without the other children making excessive fun of it, which, you know, so I assume he meant that to sting a little bit when he said it. Anyway, so a founder of all these different fields. Now, what we're going to talk about here is his halting problem. And you can already sense that it has the seeds of a paradox in it. The question is there a computer program which, if you ask it about some other computer program, any other computer program, it can accurately predict whether that other program will run forever or whether it will someday halt? Well, this would really come in handy. For instance, for a little while, Microsoft had a competitor to the Apple Music player, which on December 31st, 2008, suddenly stopped working because it got stuck in an endless loop because it was confused about the date in the leap year. To be fair, this also happens sometimes with Apple products. So if you could solve this halting problem, you could check to see if your computer is going to get stuck in an endless loop. But more important, you could do some amazing things and solve unsolved mathematical questions. Let me remind you that the prime numbers are numbers like 2, 3, 5, 7, and more. Numbers which are not anything smaller times something. They're like elementary particles. They can't be broken down by multiplication into smaller pieces. Well, it turns out that a long time ago, someone named Christian Goldbach, with a beautiful signature, wrote a letter to our old friend Euler, saying, gee, it seems to me that every number bigger than 4 is the sum, the addition of 2 odd primes. Okay, let's check. 6 is 3 plus 3. 12 is 5 plus 7. We can keep on checking bigger and bigger numbers, and this has been checked up to 4 quintillion. But we still don't know. Don't you love that? I mean, this is such a basic question. Prime numbers, even numbers, adding two things together. You can explain to a third grader that this is a question to which no one knows the answer. I'm kind of passionate about this as someone involved in mathematics education, because in the usual mathematics class, well, you get homework or a test, and the teacher knows the right answer, and the question is, can you figure it out? Here, we don't know the right answer. And I really like letting people know that mathematics has a lot of this, and not even far out, even very basic questions, we don't know the answer. Well, if we could solve the halting problem, no sweat. Because here's a program. Don't worry about it too much. You don't need to know Python or anything like that. It starts out by setting x equal to 6. 6 is the first even number bigger than 4. Then it says try all the numbers, y and z, between 1 and, in that case, 6. As soon as you find 2 where this one is prime and that one is prime, and y plus z equals x, 6, whatever, good. Now add 2 to x and go on to the next even number, 8, 10, 12, and so on. Well, if Goldbach's conjecture is true, this will run forever. It will just happily keep finding pairs of primes that add up to things, and it will never stop. But if Goldbach's conjecture is false, if there's some number way out there which is not the sum of 2 odd primes, it will halt. And so I found a counterexample. So if Turing's halting problem were solvable, we wouldn't even need to run this program. We would just ask the miraculous halting predicting program about this program. And as soon as it tells us, yes, it will run forever, or no, it will halt, we know the answer. That does sound a bit too easy, doesn't it? At least to me. That would be disappointing. That would be cheating. Well, in fact, there's no such program. You cannot predict halting. Here's why, and maybe you kind of get the idea. Well, you could ask it about itself with a twist. So let's even call it Mobius, after the twisty Mobius strip. So this is a little program where you give it another program, P, and if P would halt when given itself as input, this one runs forever. If P would run forever, this one halts. Now ask it about itself. So now it's bit its own tail. It runs forever if it halts, and it halts if it runs forever. We can't have it both ways. So this is a contradiction, and the only escape from this paradox is that there's no such program. There's no way to solve the halting problem. So now, you know, maybe when you read the leaflet and you heard I was going to talk about things that no computer can do, you thought, oh yes, enjoy strawberries and cream. No computer can do that. Well, I agree, so far at least. But this is a math question that no computer can solve. It's a question about computers that no computer can solve. So it's interesting to know that there are limits there to what they can do. I want to finish up by pointing out that there is, if anything, oh, by the way, yes, this is the Dr. Seuss version of this. I won't read it all. I'll just read the part that says, well, the truth is that P cannot possibly be, because if you wrote it and gave it to me, I could use it to set up a logical bind that would shatter your reason and scramble your mind. It goes on. This is just the first few stanzas. Okay, good. Now that we know that there's no way to solve the halting problem, this turns out to have, in many ways, an even more profound consequence. Another one of the great logicians and mathematicians who was trying to understand this in the 20th century was Kurt Gödel. So Gödel, who hung out with Einstein for a long time at Princeton later on in his life, proved something kind of amazing, which you may have never thought about it before, but maybe you took Euclidean geometry or something like that, where you didn't just have to come up with answers in math, you really had to prove them. You really had to come up with a proof. So Gödel showed that there are unprovable truths. And this is also connected to Turing's work. Let me explain. Suppose it were the case that every time a program was going to run forever, there was a proof that it was going to run forever. You with me? If that were true, we could solve the halting problem by doing two things at once in parallel. Run the program and see if it halts. If it halts, you knew it halts. And look for proofs, longer and longer proofs, that it won't halt. If there were always proofs whenever it doesn't halt that it doesn't halt, then one of these two things would be guaranteed to happen, and we could solve the halting problem. So the fact that we can't means that sometimes it's true that the program will never halt, but there's no proof of that. That's kind of interesting, because before Gödel came along, people thought, well, of course, mathematics is this branch of science where you prove things. We're going to prove all the true things. That's what we want to do. He's saying there's some true things you can't prove. To be more precise, there's no one logical system that can prove all the true things in math. Each one has some truths outside of it that it cannot grasp, no matter how powerful it is. No one system can handle it all. Is this bad news? No, this is great news. It means that mathematics will never be over. It will never be complete. It's going to be a living thing. Mathematics will never be something like this, where there's a machine where you just turn the crank and all the true things pop out. No, it'll be more like this, where we're constantly looking beyond the systems that we have. We're constantly looking for new forms of reasoning, new ways to prove things, new ways to explore, to think, and to learn. And if that's true in mathematics, it's surely true in the rest of life. Thank you.
Does anyone have any questions?
Ones that I can answer, or at least can pretend to make an effort?
Chris, thank you.
Hey.
Today, the popular press reports a possible proof of the Riemann hypothesis. I haven't yet checked beyond the popular press.
I'm sorry, I'm in the same boat, yes. So the question is, so there are several, along with the Goldbach conjecture, there are these grand unsolved questions that have been like the fixed stars in the firmament for mathematics, some of them for centuries. And one of them is called the Riemann hypothesis, and it's about the detailed structure of the prime numbers. And if we could solve that, then many other things in mathematics would fall into place. So a very distinguished mathematician, Sir Michael Atiyah, announced that he had finally proved it, and he gave a talk today. And like my friend here, I don't really know what he said or whether other mathematicians were convinced by it. There was some skepticism. But even if he has a new approach, even if he wasn't able to complete it, that would already be very interesting. He's also 90 years old, and he said explicitly in some of the press he's tired of hearing that people do their best work in mathematics by the age of 30. So he is going to prove that he can nail this unsolved problem at the age of 90. So I hope he's done it. I don't honestly know. But yes, this is hot off the presses. He gave the talk literally today.
We have a question over here.
Does the approaching world of quantum computing change any of your conclusions?
I thought someone might ask that. Thank you. So remember we had this class P, the pretty easy things, NP, the things that really require a lot of search. The majority view, although we could be wrong, is that what quantum computers can do is kind of in between. So for instance, we talked about the prime numbers. There's this basic question called factoring, right? If I give you a number 35, breaking it down into its factors means saying, that's 5 times 7. And if you could do that for very large numbers, you could, for instance, break the public key cryptosystem on which most of banking is currently based. There wouldn't be any large mathematical consequences, just the collapse of the banking system. So we know that if we could build quantum computers, we could solve that problem quickly, which is why a number of agencies with 3-letter names are trying to figure out new crypto systems that even quantum computers will have difficulty breaking. So what we don't, in fact, believe that quantum computers could solve all of the NP or NP-complete problems. And there's a lot of discussion in the press, how do you explain quantum computing to people? It's kind of true that quantum computers get to try many things at once, but that's not really it. It's more like it can be in, yes, it can try multiple things at once, but some of them, build up with each other because they're in phase, like when a bunch of light particles are all in phase, we get a laser, it's very bright. Some of them cancel each other out because they're out of phase, like your noise-canceling headphones work by producing sound which is equal and opposite to the sound that you're hearing. So what quantum computers get to do is carefully arrange this interference, as we call it, between these waves in the hope that the wrong answers all cancel out and the right answer pops out. So we know we can do that for factoring. Interestingly enough, it's not obvious what else this works for. We know that we could simulate quantum materials much more quickly than we can on a standard computer and so on. But it's still not obvious what quantum computers will be able to do. There was a meeting at the Santa Fe Institute just last year where it was a lot of fun for me because I got to have these people with these different competing technologies. There are some people at UNM who have what's called an optical lattice. This is so cool. You have a bunch of atoms floating in space, held in place by a couple of crossed laser beams. If you lose power, the whole thing just evaporates. And whenever you want 2 atoms to talk to each other, you puff them up so that their electron clouds overlap, and then they can talk to each other, and then you unpuff them, and then the information stays safe in their nuclei for like up to a second, which is a really long time for quantum things. And there were other proposals as well. These do seem to be getting now to the point of going from theory to engineering. I think that we will see quantum computers with 50 or 100 bits, which may not sound like a lot, but it's already much more than we can handle with standard computers. So I hope that answers your question, possibly at too much length.
Anyone else?
I wonder what you thought of the science paper from Cubitt and Wolf and that Perez Garcia in 2015, which addressed the same subject you're covering tonight. There's a Scientific American summary of it, but it's a 146-page proof of the impossibility of doing an algorithm to identify the spectral gap, which materials will have a spectral gap and which won't, and whether you had looked at that.
I know some of the papers around that. I don't know that specific one. It sounds like maybe we should have a more technical conversation offline. But it's true that even figuring out the basic physical properties of a complicated material, you can have this same kind of uncomputability of the halting problem sneak into that. And I think that's what you're referring to. Yeah, so for instance, you could imagine some kind of 2 or 3-dimensional crystal where each time I go from one row or layer of it to the next one, it's reading the previous row, carrying out some simple computation, and then somehow producing the next row. So it's like changing the time of the computation into space. Going downward would be like time. And then predicting whether this kind of crystal can hold together over many, many rows along a large expanse becomes asking, will this computation ever halt as it goes forward in time? And so even some basic questions like that they don't sound like computational questions at first, but you can sneak them in that way. So yeah, Mike Nielsen was on that, I think, right? Or anyway, we can talk. Yeah. Okay, great.
I have a question over here.
You described how some things that are non-obvious computations are computations in disguise.
Yes.
And I look forward to reading your book, and maybe it answers this, but are there things which are not computations, such as things that humans do cognitively, or is it perhaps the case that everything's a computation?
Sorry, are there some computations like what humans do that what?
I'm wondering what the scope of your book and your definition of computation is. Is everything a computation, since you seem to be saying that some things are computations in disguise, and for example, those things that we as humans do
Right.
in our brains?
Yeah, people debate this. So for instance, my friend Michael Lachman has studied computation in ant colonies. So, ants are communicating with each other, they're building trails, they're communicating with pheromones and so on, and they could conceivably be carrying out a very complicated computation by doing that. Now, on the other hand, maybe at the opposite extreme, when the moon goes around the Earth, is it computing anything? I mean, you could say, well, it's figuring out where it should go, but it's not clear it's doing that. It's just going there. I was reluctant at first to view the cells in our body as doing computation until I learned more about the very complicated signals they send to each other, the fact that they can respond to all sorts of different situations in different ways. So that started to feel to me like, okay, that's big enough, it's varied enough. It's not just doing one thing like the Earth going round and round, it's varied enough so that it deserves to be called computation. Now, the things I was talking about here were all grounded in, if you like, the sort of standard picture of computation, bits and ands and ors. I'm not saying that's the only way to do computation. It happens to be the way that mathematically we're the best at talking about. So, yeah, at the end of the day, I like to think of the word computation as a lens through which we can look at things. And, you and I might be looking at the same system, but if I'm a hardcore physicist, I may say, oh, well, I'm studying the energy flows in this system. That's what matters to me. But you might come in and say, wait, there's also flows of information going on in the system. So I want to view the system through the computational lens, and maybe you'll learn something about it that I won't. So I'm fairly, I'm happy to be free-willing about how we use the word. But I also like having ironclad results, that if I could magically solve this, then I could magically solve that. So if this is hard, that had better be hard too. So. Yeah.
Question over here, Chris.
There's a hand there.
Hi there, I'm over here. When I read the description of your talk and saw the word "the hard problem," I thought perhaps you might be talking about consciousness in the sense of David Chalmers's description of the hard problem. And I wonder if you have any comments to make on that, whether that's a simple problem, a hard problem, or an impossible problem.
Yeah. So let me just fill in. So David Chalmers is a philosopher who studies consciousness, among other things, and he likes to say that the easy problem is figuring out how the brain works and how all the stuff that's happening in our neurons corresponds to our mental and emotional states. He says that's the easy part. He says the hard part is figuring out, why am I in here? You know, why do I have this inner life? I mean, it's one thing to analyze a very complicated material object and figure out that it can predict things, learn things. That's glorious, but then why is there this subjective sense that I'm in here? And he calls that the hard problem. And he points out it's not really a science problem. You know, it's a philosophy problem, because you could, you know, you're not going to figure that out by sticking me in an MRI machine and doing more experiments. It's not going to get at that nugget of what consciousness is. I'm pretty sympathetic to Chalmers' view, and I regard the question of consciousness as thornier than some of my scientist friends regard it, because of this kind of remaining nugget of, well, but why is there a subjective life? It's one thing to explain how I can walk around and talk, but why is there someone here? I mean, you don't know that there is. I could just be saying that. But honestly, I haven't ever come up with an original thought on this subject. I don't know how to make any progress on it, either scientifically or philosophically. So indeed, all the problems I was saying are hard are just math problems. Some of those are really hard. So.
We have a question over here.
Hi, Chris. Thank you for your talk. I was wondering, it's kind of related to the last question, but as we do learn more about the way the brain works, and we only know very, very little right now, as I understand it, due in some part, no small part, to the fact that we don't have instruments to get inside and really see the computations that are going on in the brain. As we do that more, do you think that might change the way we look at what is hard and impossible? Do you expect there might be some mysterious new way of computing in the brain that we haven't thought about yet that would change our definition of hard and impossible computation?
Yeah, I think this is a nice question, because I mean, I think the brain does a lot of things. I think computation is only part of it somehow. But when the brain does the stuff it does, it doesn't seem that it's that much about, for instance, dealing with bits and flipping them on and off and anding two of them together or or-ing two of them together. I mean, as I'm sure you know, our neurons do combine signals from other neurons, and if the total signal is above some threshold, at least this is the kind of simplified model, then it sends a signal onto the next one. So it's doing some and or-ish things. But even single neurons are very dynamic objects. I learned this partly from David Krakauer. They're organisms, even single neurons. They're not just little wires carrying a single bit on or off. So the way that the brain computes, the way that we've evolved to do the computation that we need to do to survive, does seem to be very different from the way that we've built our computing technologies. And if we understood it better, it might inspire new approaches. And there are a couple of computer scientists who are collaborating with neuroscientists who are trying to figure out what are the basic steps of which the brain is capable. Sort of, if the brain is running an algorithm, what are the elementary pieces of that algorithm? For instance, often we have a kind of population of neurons that are all firing away, and then some other part of the brain recruits part of that population and gets them all synchronized. And I hear that this has something to do with paying attention to things. And I don't really know, because I'm not a neuroscientist, and maybe some of you are. But so these basic building blocks of neural computation may be very different from the basic building blocks of technological computation. So we should certainly learn more about them.
I think we have time for one more.
I do. I mean, the fire department agreed to unbar the doors at 9:30, I think.
Just to push further on the answers to the last two questions, how would we know if we had created a machine that had consciousness? And what does your work tell you about the hard problem of figuring that out?
Yeah, well, this is another what another one of Alan Turing's famous papers was about, right? The Imitation Game, which became the title of the movie that I have mixed feelings about. So, although I love Benedict Cumberbatch, but yeah. So this isn't clear to me either for the same reason that I didn't have a good answer to his question. I mean, the idea, Turing's claim was that, consciousness, schmonsciousness, if a computer can carry on a conversation with you about math, music, poetry, whatever, and you really can't tell the difference between that and a human, then functionally, they've got what humans have got. That was his, that's that claim. Now, again, there are lots of philosophers who are violently opposed to that point of view. There's this classic thing by a philosopher I don't find very convincing, but I guess I should bring it up, called the Chinese Room, by a guy named Searle. So Searle has this thought experiment saying, well, if I get it right, questions come in Chinese to a room, and an apparatus, a very complicated big apparatus, answers them. And it might even answer them by first translating them into English, and then was there a human involved? I can't remember. Right, so the apparatus translates them into English, and then a human answers them, and it translates it back. Okay, so then the question is, well, where in this room is the understanding of Chinese? Now, I think I would be comfortable with saying it's sort of distributed. It's the whole system, the apparatus and the human. Together, they do understand Chinese. And actually, this is easier to believe now than it was then, because now we have reasonably good computer translation programs. So now maybe Searle would like to change the terms of his thought experiment a little bit to make it something which is even harder to automate. But it's the same way. I mean, I don't view none of my individual neurons as conscious, but I think I am as a package. So now, I do also happen to believe, no offense, that I'm made of atoms and stuff, okay? So I think I'm a fantastic thing made of atoms, but I do think I'm made of atoms. So I do think that someday it is entirely possible that we could have a computer which really deserves to be called conscious. I also use the word soul when I talk about myself. I mean, I don't think it's something somewhere else, but I think it's something that kind of happens with all of what's going on in me. When I'm feeling poetic, I think of it like the beauty of a sunset. Sunsets are made of, it's a material object, but look, it's beautiful. So all of this is very far off the deep end of what I'm actually qualified to speak about. But as long as I'm up here and wearing a suit, I guess I'll inflict my opinion on you. So there you go.
Well, thank you all for coming tonight.
Let's do one more, and then one more, just
all
one,
right, I got
just
one over
one
here.
more. Yeah.
I understand now that computers are writing stories. So briefly, how did you get into this? What's your story?
How did I get into this? Well, so in, I had a computer in high school. I enjoyed programming it, blah, blah, blah. And then in college, I read a book, which maybe some of you read too, called Gödel, Escher, Bach by Douglas Hofstadter. And it was a Pulitzer Prize-winning book, and it was this tour de force where he talks about Gödel, Kurt Gödel, the logician I was telling you about before, and Escher, the artist who loved paradoxes like the staircase that keeps going up as you go round and round, and Bach, who worked a lot of beautiful mathematical structure into his music, and even some funny paradoxes where you go into it, and by the time you get all the way back out, it's not quite the key signature you went in with, and stuff like that. And so he combined, in this very exciting humanistic way, this logic and art and music. And that really got me. So that got me hooked on 1936 computer science, which was, the Alan Turing and the halting problem and Kurt Gödel. And then, you know, I went to some more college, and I kind of caught up to 1970s computer science, and by then it was the 1990s. So, you know, I eventually caught up. But I think there's, you know, in physics, there's a lot of discussion of how do the atoms of a material or a liquid or a gas combine to make a global behavior. This is kind of the style of science we do at the Santa Fe Institute. You have lots of simple things interacting, and yet some surprising global behavior emerges from that. And that's also what computation is like. Each little step of an algorithm is very simple. Each little variable is just a 0 or a 1, and yet they work together and interact in a way to solve some deep, complicated problem. So I think that interface between reductionism and holism, or between, you know, the parts and the whole, excited me intellectually. So, yeah, thank you. All right, thank you very much for coming.
Okay.